Okay, let's dive right into this explainer. Today, we're unpacking a massive scientific detective story all about the dynamic, moving ground beneath our very feet. We're explaining the chapter on the distribution of our oceans and continents, and we're going to lift these complex theories right out of the text to really make sense of them. Here's our roadmap. We'll kick things off with the continental drift mystery, dive into the secrets of the seafloor, look at the seafloor spreading breakthrough, explore the plate tectonics revolution, and finally, track the incredible journey of the Indian plate. Section 1. The Continental Drift Mystery. Let's rewind our clocks to the early 20th century, back to a geographical puzzle that literally baffled scientists for decades.
Have the continents always been exactly where they are today? I mean, when you look at a world map, it's a question that kind of naturally pops into your head, right? Have these massive landmasses always just sat there statically, or are we just looking at a single frame in a much, much longer geologic movie? Well, in 1912, a German meteorologist named Alfred Wegener boldly proposed a pretty wild idea. He suggested that around 200 million years ago, all land formed one single massive supercontinent called Pangaea. That literally translates to all Earth. And this huge landmass was surrounded by a mega-ocean called Panthalassa, meaning all water. According to his theory, this megacontinent eventually began to split into two major chunks, Laurasia and Gondwanaland, which then kept breaking down into the smaller continents we know today.
Now, Wegener didn't just guess. He fired off this incredible list of undeniable clues. For starters, he noticed the jigsaw puzzle fit of the South American and African coastlines. Then he found identical 2,000 million-year-old rocks on the shores of Brazil and Western Africa. He also pointed out these glacial tillite deposits scattered all over the southern hemisphere, and get this, rich placer gold deposits in Ghana that perfectly match source rocks all the way over in Brazil. Oh, and perhaps the biggest clue? Fossils of the Mesosaurus. It's a small reptile that lived in shallow water, and its fossils were found in South Africa and Brazil. That's 4,800 kilometers of open ocean between them, proving for sure that these lands were undeniably connected once upon a time.
But, well, here is where the theory hit a massive brick wall. Wegener had all this incredible evidence that the continents were once joined, but he completely failed to explain exactly how massive continents actually moved. He thought maybe the Earth's rotation or tidal forces from the moon and sun pushed them around, but other scientists at the time knew those forces were completely inadequate to push solid rock over thousands of miles. So his theory was largely dismissed.
Section 2. Secrets of the seafloor. To actually solve this mystery, we have to fast forward a bit to the post-World War II era. This is when scientists finally started looking down into the dark, deep depths of our oceans.
And wow, did mapping the ocean floor change the game? It revealed this absolutely massive, interconnected chain of submerged mountains and deep trenches. And what's wild is that earthquakes and volcanoes are heavily concentrated right there, especially along the mid-oceanic ridges and the famous Pacific Rim, the Ring of Fire.
Basically, scientists discovered that the ocean floor wasn't just some ancient, flat, boring plain. It was actually a really young, highly active landscape. They found that the mid-oceanic ridges were intensely active volcanic zones. And crucially, the rocks making up the oceanic crust were way younger than continental rocks. Actually, there's no ocean crust older than 200 million years, whereas some continental rocks date back 3,200 million years. Plus, the layer of sediment on the ocean floor was unexpectedly thin, just clue after clue.
Section 3. The seafloor spreading breakthrough. So all these bizarre underwater clues eventually led a scientist named Harry Hess to an absolute breakthrough in 1961.
Hess realized that those mid-oceanic ridges weren't just underwater mountains. They were literally the birthplaces of brand new ocean floor. He hypothesized that constant volcanic eruptions at the crests of these ridges actually rupture the existing crust. Then fresh lava wedges its way in, forcing the older crust outward on either side. Think of it as a giant geological conveyor belt. Volcanic eruptions happen constantly at the ridges. The crust breaks, fresh lava fills the gap, and the crust is slowly pushed outward. But wait, if new crust is always being made, why isn't the Earth getting bigger like a giant balloon? Well, Hess figured out that as this new floor spreads, the older, colder crust eventually sinks down into deep oceanic trenches and gets consumed back into the hot Earth. Section 4. The plate tectonics revolution. You see, seafloor spreading was the final missing link. It unified everything into the grand theory of plate tectonics in 1967.
Here's the absolute crucial point. It's not the continents themselves just drifting aimlessly like boats in the ocean, like Wegener originally thought. Instead, we have these massive lithospheric plates, and they are carrying the continents along for the ride. A tectonic plate is this colossal, irregularly shaped slab of solid rock made up of the crust and the rigid top layer of the mantle, and it moves as one single unit over a softer, hotter layer underneath called the asthenosphere.
The Earth's surface is essentially cracked into 7 major plates, like the Pacific and Eurasian plates, and several minor plates, like the Nazca and Arabian plates. It's like a giant spherical puzzle, and all the pieces are constantly moving and jostling against each other throughout Earth's history.
And all the action happens right at the volatile edges of these plates. This is where crust is being created, destroyed, or violently scraped together, all depending on the type of boundary.
We generally group these boundary interactions into 3 types. First, we have divergent boundaries, where plates physically tear away from each other, generating brand new crust at spreading sites like the Mid-Atlantic Ridge. Then, we have convergent boundaries. This is where plates literally crash into each other, and one plate dives under the other, destroying crust in what scientists call a subduction zone.
And there's also a third type, transform boundaries. This is where plates just slide horizontally past each other. The crust isn't produced or destroyed here, but the friction is immense, just massive slabs of rock grinding past one another, causing huge earthquakes.
So, what's driving all this? To finally answer Wegener's missing force from decades earlier, a scientist named Arthur Holmes proved that intense heat deep inside the Earth acts kind of like a boiling pot of water. Heat generated by radioactive decay and residual warmth creates these massive convection cells in the mantle. The hot, softened rock slowly rises, spreads out beneath the plates, cools, and sinks back down. It's literally the engine that drags these colossal lithospheric plates around.
Section 5. Journey of the Indian Plate. Okay, let's bring all this home by tracking a real-world example. The incredibly dramatic journey of the plate that sits right beneath India.
India actually started its life way down south as an island off the Australian coast, separated from Asia by the massive Tethys Sea. Then, around 200 million years ago, when Pangaea broke up, it began this rapid northward sprint. Along the way, about 60 million years ago, immense volcanic eruptions formed what we call the Deccan Traps, and finally, roughly 40 million years ago, it slammed directly into the Eurasian plate.
But that grand 40-million-year-old crash didn't just happen and stop. It violently crumpled the Earth's crust to form the towering Himalayas. And honestly, what's absolutely amazing is that those mountains are literally still growing taller today because the Indian and Eurasian plates are continuing to push against each other right this very second.
So I'll leave you with this provocative thought to wrap up our explainer today. The Earth beneath their feet isn't static. It's completely alive, shifting and changing constantly. Some plates are even racing at over 15 centimeters a year. So if the plates are moving right now, what entirely new supercontinent are we slowly building towards? Think about what our world map will look like in another 200 million years. Thanks for joining me as we unraveled this incredible geological puzzle. Keep observing, keep questioning, and keep learning.